This is our digital clock for Lab4. You can see it incrementing. And the second switch is a set time, which we start at 12 a.m. without seconds because the average user wants it to be 00 in any case. To show it starting, there it goes. With it being AM, we displayed it that way with this changing to a P when it's PM. To show that, here is 2360 to show that. So this will 24 and then 0 as it should be in 24-hour, and then also 0 AM as it should be in 12-hour. And then setting it to just 23 itself, 11 PM, and then 22, 10 PM, and then 20, 8 PM. We could try some earlier times. 8 AM. This first one's the mode, so you can see that works. And then 2 AM. Right there. This third switch is the alarm. And as you see, this is incrementing. We can flip this alarm switch and it still continues incrementing. And then we can set it from the previously entered time. But to do a simple example, I'm going to set everything to 0. And then here, this is going to be 12 AM. See, this is blinking yet, but we have to set this alarm input. We're going to do it to a minute after. Both to 0. And then at the end of that minute, this LED will blink again to show the alarm. And this switch is what I enabled to set the alarm after I set the time. It'll be this LED. Yep, there it goes. Okay, so the first part of this is, I'd say in this design, where, like, if we have, in this case, well, time format being 0 is when we're doing the 24-hour mode. And we're just using mod 10 because each of these are 4-bit registers. And these zeros are why that's there. But when we get to else, so it's else if, where time format's equal to 0, so that's when it's equal to 1, we have to do some logic where, like, if this result is greater than or equal to 12, we know that this is past it being AM or PM, and then 12 ends up sending to P, and 11 sets it to A. And these digits are fine because they're just seconds and minutes, but with the hours, these need to be converted. So I arbitrarily split it at 22. 22 mod 12 is 10. And then when this is smaller than 10, that's just so I have some range of how large this is in the 4-bit register. But this mod 12, where this is that second digit, that works out okay. However, when we get to the case of 22, where it's equal to 10, we have to catch the 22. per se, and then make that 0, which is this hour digit, and then this one we have to perform a different expression, which would be 22 mod 10 divided by 2, which gives us 1 in the leftmost, which we need. But if we ended up doing mod 2, you'd get a 0, so it wouldn't end up working. So that's how 10 p.m. works. And then with some test benches, this was very simple. This always just makes it oscillate, and every 5 nanoseconds the signal flips. That's why it looks like 100 megahertz. I had the same one twice. But in any case, yeah, so you can see clock in oscillating, and then the counter is being put through a flip-flop and some always block, and then you can see it incrementing, and as time goes on, it's still doing the same thing. Then the last interesting thing, that's unfortunate. With the CDA playground, let's run this. Oh, I see. This is a 7-segment display, so this is the test bench for the top module, where we just throw some random integers into these registers that fit the size of the bit width. And all the inputs, like these ones, these are all just set to oscillate. So that's what that looks like. You can see the integers being placed.
Okay, first we have our clock division model, which receives 100 megahertz clock, then converts that clock into 1 hertz clock. So basically we set our parameter division as 100 million, and every time when 100 megahertz clock is high, increase counter by 1, and then when counter becomes equal or greater than 100 million, we set counter again to 0. And then since we only counted when 100 megahertz clock is high, we have to double up the frequency of clock to make it as a 1 hertz clock. So we set as if counter is smaller than 50 million, then the clock becomes 0, and then if it's greater then becomes 1, set it as 1. And now we move to clock, which basically have function only same to ALU and clock itself. So it receives clock reset and like setting options and some input values for set time and also set alarm. So we observed that the clock that we divided in previous model was actually faster than we expected. So again, we tried to adjust clock by slowing a speed to 1/3 of it. So then we moved on to basically functioning the clock itself. So if set time is equal to 1, and if set is equal to 0, which will be equal to set time, we set our current time, current minute, current second, just registers to our input values. And if set time is 1 and also set alarm is equal to 1, then we set our alarm and alarms equal to our input values. And if else, then we just created basically just clock functioning. So every second you increase second by 1, and then if second becomes greater or equal to 59, then increase minute by 1 and set second as 0, and then so on. And we converted our current hour, current minute, current second into single digit number. So the first digit of second 0 is the value. That's second remainder of second by 10. And the second digit, 10th digit of second will be equal to second divided by 10, and so on. And if current hour is equal to the set alarm, then the light, we set light to blink, and if not, then light stays as turned off. And that's it. Thank you.